So, I would like to welcome all the students who have taken this course Mathematical Methods 1, which is very important in physics because it deals with few mathematical techniques we always use in physics. In this particular course, however, we only restricted ourselves to two very basic topics. First one is linear vector space and second one is complex analysis. So, linear vector space is very important in understanding the quantum mechanics because in the higher class when quantum mechanics is deal with this Dirac notation and all these things, the fundamental aspects of linear vector space is very important. On the other hand, the complex analysis is equally important because in many branches of physics, quantum mechanics or in other branches of physics, it is invariably the linear the complex analysis is used. So, complex analysis, complex numbers is a very important concept that we should learn also. So, let us start with linear vector space. So, as I mentioned, it is very important for the learning to learning to this quantum mechanics. So, let us start with a very basic concept which is set. So, set by definition it is something like a collection of well defined a collection of well defined objects or elements which are distinct. A simple example like if S is a set containing the numbers 1, 2, 3, 4, 5. So, the extension of these numbers are up to 5. So, I can say any general element x which is belong to the set S is restricted by this thing. 1, 2, 3, 4, 5 is however the natural numbers. So, 1, 2, 3, 4, 5 and so on is a set of natural number, we call it natural number. Similarly, we can form different sets. For example, the set of all real numbers, set of all real numbers, normally we defined as R, which contain the numbers minus infinity to plus infinity. All the numbers are the set of R inside. Next, I can say in the similar way that set of all integers. Normally, we write at Z. All integers I can write inside this set Z as say minus 10, minus 9, so on, 0, 1, 2, so on, 9, 10, so on up to infinity. Only the integers with positive and negative values. In the similar way, a set of all say rational numbers, we write it as Q, where the elements can be represented in the form of P by Q, where P and Q belongs to Z. We know that if a number is represented P by Q and if P and Q both are belongs to these integers, then this is a rational number. Similarly, the set of all complex numbers, this is an important set we are going to use later. So, all complex numbers in the form A plus IB, where A and B belongs to the real numbers. A, B are real, but as a whole A plus IB is a quantity which is inside this complex number. So, this is a different kind of number, however. Similarly, you can form different kind of sets, like for example, rational number. I can also have a set which are irrational. For example, root over of 2, pi, etc. These are the quantity which are irrational. That means it cannot be represented in the form of p by q, but this is a real number. So, this can also form a set. So, with this example we try to find out that there are many kind of set that is present, and it is defined in this way. After having a knowledge of sets, next important thing we need to know is called the binary operation. Binary operation is some kind of operation that we need to define over a set. So, set I already defined, there are few collection of numbers, they are well defined and distinct. Now, the next thing is that we need to understand that some kind of operation should be on this particular set, and as a result we will get something. So, let us put some kind of definition in the form, say I call it binary operation. Sometimes it is called binary composition also. The composition and binary operation are same thing, which by definition says that if this correspond to some operation and I operate this star over two elements of a set, say a set has some element A, B, C and so on, and I want to operate this star over these elements like that, A star B, then I will going to get some other element C. Now, the binary operation by definition is that C, if A and B belongs to the set S, then C has to be in S also. So, that means if I operate the binary operation over two elements A and B, whatever the result I find here, for example, I find C, this has to be inside the set. It will not going to be something that is outside the set. What will be the example? For example, I can write this as plus operation. Now, I define this general binary operation to a particular operation, say plus, which is addition. Now, after having a binary composition, we need to know over which I need to apply this, what is the set over which I am going to, on which I am going to apply that. So, I am going to take a set real number. So, real number, as I mentioned earlier, it contains all the numbers ranging from minus infinity to plus infinity. If now I operate this plus operator over any two elements, for example 5 plus 3, it will give me something 8. If you do this exercise for whatever the element you like, you will always find that the end result that I am getting after applying the binary composition is an element of R. So, this is a valid binary operation, and when the set is defined as my real number set. So, now take another example. I will going to change these things, say minus. I can always do that. Instead of taking the addition, now I am taking a operation, say minus. If I take a operation minus, then I will going to apply that on over the set of natural numbers. So, natural numbers I just mentioned earlier, it is a set which contain 1, 2, 3, 4, 5 up to infinity. These are the set of natural numbers. Mind it, there is a difference between the set of natural numbers and integers. Integers also contain the negative values of 1, 2, 3 and so on, but for natural numbers there is no negative, and also the 0 is absent. Now, if I operate this minus operator over there, for example, I take 3 minus 2, where 3 and 2 are the elements of this set n, and I am operating this binary operation minus over 2 elements 3 and 2. As a result, I will get 1. You find that in this case, at least for these 2 elements, after putting the binary operation, I am getting something which is inside the set, but it not necessarily be true for all the elements. For example, what happened if I do 3 minus 4? Again 3 is the element here, 4 is the element here, minus is my operation. I will do 3 minus 4, I will get something which is minus 1, which is outside of the set, because minus 1 is not inside the set. So, even though my binary operation is well defined, my set is well defined, if I operate this binary operation, I will find that the result that I am getting is outside the set. So, this is not a, at least this operation is not a valid binary operation for this particular set. Okay, so now I know what is the binary operation and what is the set. Now, a more important concept we need to know. We know what is binary operation, we know what is set, the definition is clear to us. Now, the next thing is that group, the concept of group. It is a very important concept in understanding many things in physics, and also in mathematics the concept of group is very important. So, let us try to find out what is the meaning of group. Say G is a set containing the elements A, B, C and so on. Now, there are few properties that the set G has to follow if this set G form a group. What are this property? First property, A star B is equal to belongs to G. By the way, when I say group, when I define a set, then I also define a binary operation. Here consider star is a binary operation. I do not know for the time being what is the star, it is plus, minus, multiplication, I do not know, but this is an operation that I operate over 2 elements and I am getting something. So, the first thing is that A star B, I operate 2 elements with a binary operation and then I am getting something that has to be inside G. So, this is by definition, this is true, because binary, the definition of the binary operation is that only. It is called the closure property, closure. That means I operate a operation over 2 elements, whatever I am getting is inside the set. So, it is a closure. 2, A star B star C is equal to A star B star C. So, I first operate B C and then after that I operate that quantity with A. This is the same thing that I operate A B first and then operate with C. So, this is called associative. So, first one is closure, second one is associative. These two rules has to be followed by G if it forms group. Anyway, there are other rules also. The third rule is A star E is equal to E star A is equal to A. A is an element of the group, E is the element of the group. Here I should write A, B are element of this group. Here A, B, C are the element of this group. Every time you should we should note that all the elements that I am taking is from this group and that is trivial. So, here also E is some element that is inside this set G. So, E belongs to G. Now, this suggests that if I operate A with E, I will get back to the same element. So, this is called the identity. It's like this particular element behave like a identity. So, existence of identity is important. This is called identity. So, inside the group I should have, it essentially means inside the group I should have some kind of element here, for example E, which behave like in such a way that if I operate any of the element A, it will return back the same element here. For A star where A star is also an element of G. This A prime also is element of the set G, and I operate this A with this A prime, and as a result I am getting back my original identity element. So, this is called the existence of inverse. So, inverse should exist. Now, if this 4 property is satisfied, I now defined a binary operation, I defined a group, and now I operate this binary operation and check whether these 4 properties are satisfied or not. If it is satisfied, then I must say that this particular set G forms a group. However, apart from these 4 properties, there are another property which is not essential to be a group, but which is important to know, that A star B is equal to B star A. If that is true, that means I can reverse the operation. I first take A and then operate over B. Whatever the result I will get the same thing if I just exchange this element. I take B first and then A, and I will get the same thing. It is quite it seems to be quite okay, but it is not true for all the groups, different groups. This property does not hold always. If it is hold anyway, then we call it is the commutative property. So, this is an additional property. This is an additional property. If a set with binary composition star, if has this additional property, then we call a special name to that group, and this name is called abelian. This group is called abelian group. So, the important thing that to be remembered, that the group formed by the set S under the binary operation star, if this 4 property need to satisfy, if they satisfy, then we will say that the set G are forming a group under the operation star. Apart from that, if the extra property is satisfied by the group, then we call this as abelian group. So, we can have a very simple example of formation of the group. There are many examples. So, let us start with a very simple example. So, in order to put the example, I need to first define a set, and then I need to define a suitable binary operation over that. So, let us say R is my set, minus infinity to infinity, all the numbers. So, I define set, and what will be my binary operation star is equivalent to the same thing, plus addition, simple addition operator I consider to be my binary operation star. Now, I apply this over the elements over that. So, you can readily understand that any element A plus B, if I do, it will be belongs to the real number R. This is quite trivial, that if I add 2 things, whatever the result, 2 real numbers, whatever the result I will get, that will fall in the real number. example 2 plus 3 is equal to 5. You can take any number you want. Second thing, A plus B plus C is equal to A plus B plus C. This is also true. If I take another element 2 plus 3 plus 4, this is equal to 2 plus 3 plus 4. True. Third thing, it is important. So, A plus 0 is equal to 0 plus A is equal to 0. So, 0 in this case behaves like a identity element. So, that means if 0 belongs to R, I should write 0 belongs to R. So, this is not an element that is outside R, but if I add these two things, I will get back, sorry, here I should write A. So, if I add these two things, I will get back my original element A. So, that means the identity is there. This is my identity. Fourth thing, so I can write this as this. A is any element I want, minus A is again an element which is inside the set R. Now, if I add these two things, I will return back my identity element. So, minus A here is the element which we should call is the inverse in plus operation. So, all the four properties is satisfied when I take the real number set and addition. So, I can say, however, the fifth operation A plus B, B plus A, fifth property rather, it is also satisfied here. In this case, it is also satisfied. If I see, you will find that this is satisfied. So, if it is satisfied, then I can say that under addition operation, this real set form a group. It is not forming a group, we call, since this commutative relation is also valid here, we call they are forming an abelian group. Okay. So, now we have a very rough understanding of what is group, and with a very basic example, with a very simple example like addition and all these things, but there are other examples also. So, let me do that here only. So, it is not necessarily that always we take the operation addition that we know, that add two real numbers. It may happens that the addition is different. For example, let us consider the R2. This symbol suggests that I am dealing with some space. This is called the Euclidean, this is plane, Euclidean plane, where the vectors are defined. These vectors, so let me first say these vectors. Vectors is something which has amplitude and direction. It has amplitude and direction. If these two things are there, we call some quantity vector. We know that, I mean, in 2D a vector is defined like this, say alpha is a vector, another vector can be defined like this, say beta. In 2D they have two components. We will come back to this point in more general way later. So, let me first try to explain you how this group, how this vector can form a group under this addition. So, now you should remember that this addition is not a simple addition. So far we deal with the addition of these real numbers, so we know that how to add. But if I say that my group, my set, vector set is defined by these numbers, and my star binary operation is addition, I must say this is a vector addition. this is a vector addition. So now under this vector addition we will quickly check whether this under vector addition this set V forms a group or not. This is very important. So let us start with this. Add, this belongs to V. If I add two vectors, I will have another vector, say here, say gamma. So if I add two vectors, I will find another vector that will be inside this set. So this set is all the vectors you can imagine this inside this set. So first property is hold, second property. If I add two vector beta and gamma and then add the another vector alpha, I will get the same result if I add alpha and beta and then add gamma. It is trivial. Third property, very important, alpha is a vector, theta is which? What kind of vector it is? It is basically a null vector. We know that there is something called null vector. Here theta is null vector. So it is a special kind of vector which has direction but zero magnitude. So if I add these two things, whatever the thing I will get is just the original vector. So that means here null vector is my identity under this vector addition. Fourth, alpha plus minus alpha. Now if I add two vectors, one is alpha and another is the same vector but with a negative sign, that means in opposite direction. Now if I add these two vectors, then essentially I will get something is null. So again I can have this vector here. So that means identity whatever I have, I can return back this identity here with a 4 and this now behave like a inverse. So all the 4 properties according to the definition of the group is followed by this vector addition, which is not entirely the addition that we know. This is a different kind of addition. You can see there is a rule of this addition. However, here you should also note that alpha plus beta is beta plus alpha. This fourth, fifth things are also valid. If that is the case, then we can also say the vectors can form a group under this vector addition. Okay, so for this class, I would like to conclude this class here. So very important few concepts we learned here. First, the concept of set and binary operation. Binary operation is something when we apply it over a two elements of set, then I will return back something which is inside the set, that is one. And secondly, the group. The set can form a group when they follow few properties, which is closure, associative, existence of identity, existence of inverse and so on. If they follow these rules, then I will say that this particular set can form a group. In our next class, we will extend this idea. We will learn more than group. There is something called ring, then field, and finally we will try to find out, applying this concept, how the vectors, the concept of vector space emerge. So with that, let me conclude this class. So in the next class, as I mentioned, I will start from here. I will start define something called ring. Thank you for your attention. So that's all. So just wait for the next class.